Hi, my name is Aditya and I am the CEO of Automatski. Automatski makes the most powerful quantum simulators, annealers and computers in the world. Today I am going to demonstrate our quantum annealer to you and I will keep it extremely short. I assume that you already know the theory and the applications, and I also assume Automatski has given you the context of this video. So you will understand what I'm going to show you. If you receive this video by mistake and don't know what this is all about, just ignore it. I'm here to tell you what we have achieved and not how we have achieved it. All our millennium breakthroughs are completely our own inventions without absolutely any collaboration or help from anyone else. Our the implementation details of our inventions will be secret for the next 1,000 years. If that doesn't work for you, then you can stop watching this video. Okay, let's get started. What is a Cubo problem? What is an Ising problem? A Cubo problem is basically a quadratic formulation of an optimization problem where two variables at a time multiplied by a parameter form an expression, and lots of these expressions need to be minimized. This is something like minimization of energy, etc. And this is done on a quantum annealer or a digital annealer. Some people try to solve it using Markov chain, Monte Carlo, classical method, which is a classical method, or other methods like simulated annealing, etc. But those don't work very well. That is why we are looking at quantum phenomena to solve such optimization problems. And the difference between a Cubo formulation and an Ising formulation is that the values of the variables in Cubo are 0 or 1, and in an Ising formulation they are -1 and +1. Ising formulation is more easy to match to a physical implementation. So Cubo is usually transformed into an Ising model and then executed on a quantum system. Let's see what this problem looks like. So you have variable number, index of variable number 1, index of variable number 2. Here both the indexes are the same, so there is only one variable, and the weight parameter. This is one expression, plus the value of the second expression, plus the value of third expression, and so on. And this is the entire list of all the expressions that put together need to be minimized. So here the variable number 10 is multiplied by the value of variable number 17 multiplied by 138.2651 to get a value, and all these values put together, the sum total needs to be minimized. This is a quadratic formulation. So at Automatski we benchmark such problems, and we are probably the only firm in the world which benchmarks such problems at large scale, like 10,000 problems, 100,000 variable problems, 1 million variable problems, 100 million, 800 million, 1 billion, and in some cases we are also looking at a trillion qubit or variable problem. Now this setup is a test setup, it is not a production setup. So our physical hardware is connected to this development environment, and if this you can recognize, this is Eclipse Java environment. We expose our quantum systems as a remote service which can be accessed by various programming languages like Python, Rust, Java, Mojo or whatever. So that is not a problem. I was saying this is a test environment, and this is 1,000 times slower than a production environment, but it is also 100 times cheaper than a production environment, and this allows us to test problems at scale without getting precise solutions or 100% accurate solutions. The production environment will give you literally perfect solutions off by just a few bit flips. So this is a test environment. Okay, so let's look at a 100 qubit problem, and let me show you. Yeah. So here it solved the problem, and this is the best energy it got. While in quantum systems you have to sample it also, right? And so it does this like you know, uh, iteratively, and you can give it a time limit to solve a problem. Okay, let me look at a slightly bigger problem. This is 100,000 variables, and uh, even though the test environment is 1,000 times slower than the production environment, it is still very fast for mid-size problems, and you can see it is converging very fast to the global optimum. I'll stop it here, and all of this is dumped into a solution file which can be interpreted or used in your formulations. So this is, if you see this is 1 million qubits formulation, and like I said, 1 million qubits for us on this test environment is a mid-size problem. The system, my classical desktop system loads this problem. Remember this Cubo file? This is the kind of file which we'll load onto the quantum test environment. And the loading takes a lot of time, because for a million qubit problem, the file size is very big, and it needs to be processed and reformatted and transformed and then loaded onto the environment. Okay. So now for a 100 billion Cubo problem, I can try to show it to you, but what I'll do is, since it takes 14 or 16 minutes to load, we can't wait that long. I'll show you some pics of it working. Look at this picture. This is from the file system. These are various problems, Cubo problems, QAA problems. And here, this is the 100 million Cubo problem. It is a 13.314 gigabyte, problem statement file. And this is how it runs. We have run it and we have taken snapshots. Remember, this is a test environment. This is 1,000 times slower. So for a 100 million qubit problem size, you can see this running here, and the solution is converging. Before that, at 60 steps, it was here, minus 2148, and it started off like this. This problem got loaded, and it started execution. So it is retrieving the intermediate solutions at intervals of 36 or whatever seconds. Now, the last thing I want to show you is that QAOA problem is also an optimization problem formulation, which has different problem types, which can be used to solve different problem types like max cut, etc. Now, max cut, max K cut is basically a graph coloring problem, which is NP hard. All of this is NP hard, by the way. So I'll show you, just for the sake of demonstration, that this quantum system of ours, even though it's a test environment, can also solve QAOA problems, and a circuit-based quantum computer can never beat an annealer when it comes to optimization problems. I think that race is over now, because the speed at which annealers are scaling, it's very difficult for circuit-based quantum computers to catch up, and especially just to solve optimization problems. Quantum annealers are cheaper and more precise and have a very huge scale advantage. So let me show you. So in a max cut problem, you try to maximize the cut so that I'm sure you know about it. Okay. So here it is converging, almost there. I said we'll be off by a few bit flips at worst. So we are off by 1 bit flip here, 1 or 2 bit flips here. The optimal solution is 5434. I'll stop here. Okay. That's all we had for today. If you have any questions, you can email us at info@automatski.com. Thank you so much.